Hello. Thank you to the organizers for this opportunity, because I always only get to do talks which are about products or about deltas of products, but I never really get to do a basic what is a queue talk. And so I put this into the CFP, and they actually took it, and that is fantastic. So I will assume that none of you know what a queue is. There is grumbling. All right. Maybe some of you who know what a queue is will be able to follow, but those who know what a queue is are messengers. And I'm going to trick you by starting this talk with a few pictures and make you think that it's going to be easy, and then I will exhaust you towards the end of the talk. So, messengers have a long history, and queuing is the modern form of messaging. We are the messengers, we are the postal service of IT. We move data from A to B, and we do so in envelopes, as I will explain to you. So this lady who's sending a love letter, or just got one, is a messenger. Messengers had an important role and still have an important role in all kinds of areas of the world, and especially in earlier days, kind of in war efforts, that's the way how communication happened. Like in the First World War, for instance, this is a soldier, a French soldier, holding a carrier pigeon. That was the way you communicated. You communicated asynchronously, obviously, because the carrier pigeon would only go one way. And you would kind of semi-reliably communicate because the pigeon might get shot or eaten. Postal service was effectively initially what made the world smaller. Right? We had telegraphs, etc., but if you have more substantial data, the highest throughput, the most data you could send was done through mail and then eventually through airmail. So these were all messengers. And then, of course, we had telegraph services, and then we also had a combination of telegraph services and motor couriers, which means messages were transmitted from post office to post office because that's where the electronic equipment was, or electric equipment was, and then messages were written down on telegrams, and those telegrams were then delivered by mail. All of that asynchronously, because that was the way how things worked, right? You send a letter, and you get a letter back. The nice thing about this, about these asynchrony, is that it scales. We have learned over a very long time, humanity has learned over a very long time how to scale communication using asynchronous messaging. And in computing, it's kind of a lost art, and it's a little sad. Queues are also not something that is foreign to none of you who just showed up at this conference this morning, because I was able to go through the fast lane. I'm sorry. But many of you weren't, so you stood in a queue. And that's the only way how you can make the registration desk scale, because it doesn't make sense. It would be nice, but it doesn't make sense to have 1,000 people standing at the registration desk. You have to scale it to some level, and then the queues, how to make that all work. So queues, like you were in a queue, that's how you create scalability. That is how you manage a small set of resources, 20 people doing a registration at a registration desk, and deal with 5,000 requests to those resources. You queue up, and you naturally know how to do this because you all did it. The same organization happens pretty much everywhere in life. We have airports that queue up airplanes for departure. They have to do that because airports need to have a runway, aircraft need to have a runway, and there's only one or two, which means they need to share it. It's a shared resource. Therefore, we queue. And of course, you all know this from traffic, right? If you want to go from A to B, there is not asphalt covering the entire space, so you couldn't just go and drive. No, there are roads. And if The roads are overtaxed if there are too many cars. Queues form to get you from one place to the next. So it's a natural way of how we do things. However, many of us are not using queues explicitly in computing systems, and that's kind of funny. So I will talk about message queues. I will talk about queues first, and we'll talk about message queues, and then I will go into some feature survey, which I will anchor on the products that my team builds. But all the knowledge that I'm going to give you today is usable for AWS, for Google Cloud, for RabbitMQ, for any of those services. I'm not going to do a product pitch here, but I really want to teach you what a queue is and what the features are. All right. I'm going to start in a very unusual place here. Most developers that deal with applications have a notion of implementing a function call. And never mind the shape of this here, right? It's not important that this is a C function, or it could be a C# function, or it could be a Java function. It doesn't matter. It has curly brackets, and you might be a foe of curly brackets. It doesn't matter. It's a function. That function translates into some machine code. I have here chosen the Intel x86, x64 machine code. So this function translates into that machine code. Why do I choose machine code? Because I just want to talk about the CPU a little bit. So what happens when you go and compile this code into that machine code, which then translates really into bits that you can go and run on the CPU? How do you execute that? You give it to the CPU. How do you give it to the CPU? You put it into queues. The way how the scheduler in your operating system works is that there are many programs, and those many programs need to be executed somehow. There is one CPU. Maybe there are two CPUs. There's one core. Well, in reality, even on our phones, there's now 4 cores. But it's a constrained set of compute resources, and the way how the operating system deals with them is it goes and puts the jobs into a queue. What does it do? There's a job queue where when you want to execute a program, more precisely, if you want to go and execute a thread of a program, then you put that thread into the job queue and say, hey, can you go and execute that for me? What the scheduler will do, and that's what it's called scheduler, is it's going to go and give you a slice of time in which you get that core. And during that slice of time, you get to execute these instructions. And at some point, the scheduler will yank that from you, that control, right? And we'll put another thread in there. The job queue is how you get in line, and then there's a ready queue, which is for all the threads that have already been loaded and which are already have information in the cache, because you need to be close to the CPU. You have memory information in the cache of the CPU, so you're ready to execute. As soon as you do, so that's the second queue. So there's a job queue, there's a ready queue. The third queue is the I/O queue. Whenever you do I/O, something that's far away from the processor, far away from the core, you need to wait. And while you wait, the processor can do something else. What is I/O? I/O, for instance, is main memory access. Main memory access is 100 times slower than accessing the local cache. And of course, accessing a disk, an SSD, even the network, takes tens of thousands of times more time than accessing the local cache, which means as soon as the thread tries to reach into memory, as soon as the thread tries to reach into an I/O device, the processor, the scheduler says, hey, you're going to go on the side, you're going to go into the I/O queue, and once your I/O queue is done, we're going to put you back into the ready queue. So when you're executing code, you are already using at least 3 queues. And you didn't think of that. Thread pools, if you're using an HTTP server, who's using an HTTP server? Whoever is leaving their hands down is lying. Okay, so Creating threads is expensive. Why is creating threads expensive? Because you allocate memory, you allocate a stack, we have to do the work of the allocation. So that is all expensive work that needs to happen. It takes a few microseconds, and we're all greedy. Which means if you have work that is all of the same form, like processing HTTP requests, you make a set of threads, 1, 5, 10, however, and you keep those running, and then from the application, you execute callbacks on them. Who was doing JavaScript again? All of you are using thread pools. All of your work executes in Node.js, JavaScript, all of that executes on the thread pool. It's one thread belonging to your process, and that process gets all the work. You're also using a fourth queue. Remote function calls, REST calls, gRPC calls, anything that goes across a process boundary, anything that goes across a network boundary needs more infrastructure. The add function gets translated into a request and into a response. Those are messages that are being formed that are sent through a network through magic means. The magic is being held by a proxy, which sits on the caller side, and by a listener and dispatcher, which sits on the callee side. On the callee side, those messages are being dispatched, meaning they're being assigned, somehow magically matched to code, which causes the code to be executed. And that's the 4 queues we already talked about. So what's the listener and dispatcher doing? And I'm only showing the listener here. The listener sits and hangs on, accepts the connection. So someone connects. Connecting over TCP/IP with HTTP, HTTP2, any of your protocols, right, shows up on a server. That server may be busy. So it may already have 100 connections that are being currently worked on, or 1,000 connections. The server it's in the server's interest not to get overloaded. Right? You don't want to have the server too busy thing. So the server will try not to accept more connections it can deal with. How is that handled? All the connection requests go into the accept queue of the TCP stack. And so these connection request packets, effectively the SYN packets, lie there, waiting for someone to go and pick them up and say, I'm OK to go establish that socket, and then only then that socket is being created. It's a defense mechanism. The server can go and control how many connections it processes by just taking what it can from that accept queue. That's why we have that queue. Now, once you have that accept queue, taking a request, taking a socket, the socket is getting established, basically the handshake completes, and now you have 2 queues. A TCP input buffer, which contains everything, all the messages, all the bytes actually being sent to you, nicely, neatly organized in order. That input queue exists because messages, packets actually get lost on the wire occasionally. And so if they get lost on the wire, they need to be resent so that you have a consistent sequence of data, right? Packets get lost on the way all the time. So TCP, that protocol, maintains this queue, and with that, makes sure that you only get this consistent stream that is in order as intended and will recover packets for you on the way. And that's the buffer, ultimately, that's being made available to your application that you can go and use. Another queue. When you're sending, there's obviously an output buffer that you're sending into, and that will push back, will not accept further messages when bandwidth is low and when it can't go and send. I'm not going to explain the entire TCP protocol for you, but those are 2 queues. Once data comes down that input queue, there is an HTTP listener, and that HTTP listener will now go and observe the stream, will kind of start, oh, this is the start of an HTTP request, and this is the end of an HTTP request, and as soon as it finds the start of an HTTP request, what it will do, it will take that HTTP request and put it into yet another queue. Because there's an HTTP listener, an application sitting on the other side, a pool thread, and that pool thread will now read from that queue, from the incoming HTTP requests, and will go and take them across multiple sockets. So all the arriving HTTP requests across all established connections, they kind of land in that input queue, and then you can go and read from that input queue. So how many queues do we have now? I'm kind of at a dozen or so, depending on what your operating system is, what your stack is. You will have a dozen, maybe you have 20 queues that are already doing work when you're doing an HTTP request. So when you think you're using a synchronous API, you're not. What you're doing is you're using a illusion that's being created for you through multiple layers of asynchronous communication. And unfortunately, lots of the capabilities that those queues give you are being abstracted away. You're sitting behind this whole stack of asynchronous mechanisms, and those asynchronous mechanisms give you load balancing, load leveling, we're going to get to that, capabilities. But because you're using an RPC abstraction, ultimately your application is still going to be on fire when you get too many requests because you have no way of defending against it because everything is being pushed on you, with the stack gladly ignoring any of the busyness and business you might have. That is kind of sad. So I will propose that you take your faith into your own hands, and your fate into your own hands. Take your fate in your own hands and use a message queue explicitly, occasionally, because that's going to help your application. So I'm going to explain that. Now it gets a little computer science-y, but that's OK. You're here, and you came here voluntarily, so now you have to endure a little bit of computer science-y things, but that's fine. So what is a queue? I also wore a jacket so that I'm a proper professor. So the queue per se, and that's the queue we've so far talked about, is one of the most fundamental, most important data structures in computing. It is the thing that makes everything work in operating systems. It is the most fun, because it's the most dynamic one, right? An array is boring, a dictionary is boring, a tree is boring because you only store stuff in them, right? But a queue actually moves things. That makes it super cool. Moving things is great. All the other data structures are boring because they're static. Queues move things. So it's a sequence of records, commonly ordered by the moment of arrival. You write to the bottom, and you take from the top. And when you've taken a message out, that message is gone. So it's a write-only structure from the bottom, read-only structure from the top. And it gives you order. What's most important, though, the most important feature, as you'll find, is taking something from the top and that thing then being gone is the most important quality of a queue. Because that means that only one party can ever get that item, because otherwise it's gone. And what's also important, as we'll find, is that you can always observe the length of a queue. You will always be able to tell how many items are in that queue, and that is super important. Example, this morning, when you were standing in that queue, you could kind of guess and tell when you would about be having to go and take your registration materials out and then finally be through that queue. But also, the organizers could tell whether they have to have more staff or less staff dealing with that queue. And they have to staff maximum up to deal with that big queue. And if they now look outside, there's no more queue, which means they probably only have 2 people. Because you can observe the length of the queue. So it's a very practical thing. Being able to observe the length of the queue is important, because that will be an indicator of how much work is currently, what the capacity of the system is that's left. If the queue is empty, you have plenty of capacity. If the queue is long, you don't have enough capacity, you may have to go and add some. There are some variations of queues. There's priority queues. Again, I also mentioned that earlier already. I went through the fast track because I'm speaker, and they let us do that. It's mighty unfair, okay? But it's a priority queue, right? There's a priority queue, priority 1, speakers, exhibitors, other people who give the organizer money. More money than you. And then there's priority 2, which is everybody else. And that can be done in 2 ways. You can have 2 queues, which I find smarter, and which is the way how this is done here, right? There are 2 separate queues. And there is no, oh, you are special, and therefore you now get to rush in past all those people in this one queue, because there would be fights, people would be unhappy, etc. So that would not be a good idea in a practical life. But in computer systems, there is this notion of priority queues, and when you think about what thread priority means or process priority means in an operating system, right? You have these high and low priority. What that means is that the scheduler items in that scheduler queue are labeled with these priorities, and then the things that which are higher priority rush to the front. So it's one queue, different priorities. And then there's also a multiplex queue. And a multiplex queue is being used if you have one communication channel that has a form of a queue, but you have multiple contexts which flow through them. Think of HTTP2, HTTP3. You have one connection, but HTTP2 and HTTP3 actually reuse that connection for multiple concurrent connections or links. AMQP, the queuing protocol, is exactly the same. So you have these scenarios where you have these different contexts which need to go through the same channel in some way, and that's also true for queues in many ways, where you got to go and multiplex through those. So that's possible too. And it's a feature you will also see in forms of message groups in queuing products. So finally, after all this setup, I can get to what a message queue is. A message queue is all of the above, plus it deals with messages. So it accepts and stores and then makes messages available for consumption. And this accepting business is quite a serious one. Message queues come in various forms, but the most common ones and the most popular ones are implemented using message brokers, and those message brokers take pride in not losing any messages. The queues we've talked so far about, CPU, etc., scheduling queues, etc., when you turn the power off, all of that is gone, obviously. Well, if you have a message broker, the message broker will go and take a message, like mail, and then no matter what happens, it will not lose it. At least it will try to. And of course, that depends somewhat on the failure characteristics of where you run your broker. If you run your broker in a container, in a Kubernetes cluster, and the Kubernetes cluster burns up, well, then all your messages are gone too. If you run that in a PaaS service in the cloud, then it's far less likely that the messages are getting lost. But a message queue is insurance for your systems that if you want to go and send a message from A to B, that message is safe. And it's insurance that if you have a process that's using those messages and that process crashes, those messages are still going to be there. So message queues are a reliability feature for your applications. It accepts, stores messages, and holds onto them until you consume them. And certainly, if we're talking about cloud brokers, Azure Service Bus, AWS SQS, Google GCP, they make those promises. None of those brokers will lose a message. You store them, you store that message there, you can go and retrieve it later, and it won't be gone, unless you wish to. That's something we can also do. A queue, and these 3 next items are super important. A queue individually manages the life cycle of every message. A message can be accepted. Once a message has been accepted, it's moved into the available state. Available means it can now be consumed by consumers. Once it has been consumed, it is archived or deleted. And then it may also be rejected. We're going to see what we do with that. So it has states it goes through, and the broker, the message queue, has a feature. It, as a feature, manages that. Messages are also exclusively acquired by one consumer, which means if you want to schedule work, work is usually done once. And if you want to make sure that in a distributed system, that work gets only done by one party, but you need to have 1,000 desks in which you can process registrations, you have 1,000 processors in which you want to go and do work, then you need to have a tiebreaker, you need to have a judge on who gets what work. The queue is that. The queue gives that work to one consumer. And as I said, the length can be queried. In the message queue, run messages. We're going to get to the messages in a moment. Okay. This is a very important point that I want to make at this point. Apache Kafka is not a message queue. If you believe that you're building a modern messaging infrastructure with Apache Kafka that has queues, or if you call a Kafka topic a queue, you're wrong. Kafka doesn't have individually management of lifecycle of messages. You cannot query the length of the queue because you don't know what the consumption status is. And messages are not exclusively acquired by one consumer. They're always acquired by a consumer group, and that consumer group can scroll back and forth over that message stream. There are no queue features in Apache Kafka. It's not a queue. And I'm saying that here because I see in modern infrastructures Apache Kafka being used as the queue, and it's just not right. There are other products, I'm going to name a few, that do that work, and it actually has its place as an event stream engine, but it's not a queue broker. Take that home with you. All right, so what is a message? A message is an envelope that is annotated with metadata around the data structure that you want to have move between data and apps and services. So let's start with the data structure. The data structure is the letter you want to send between two applications. It might be schematized, Avro, protobuf, thrift, whatever your encoding is, JSON, XML, whatever that is. A message broker typically doesn't care, it moves byte arrays. And that message may be end-to-end encrypted. So the message broker, the queue, has no opinion, typically, about what that payload is. It doesn't look into your letter. Because that is so, you need to annotate that message with a little bit of information so that the message broker or PubSub infrastructure, but also the dispatch code, meaning how that message gets from the queue into your application, that has some information to deal with. And so that is metadata. Metadata is the to of the message, the subject, or sometimes a type, or a content type, or a correlation ID. These are all attributes with which that message is decorated. And if you want to have an image of that, of how that doesn't actually look, but to memorize that, think of this. Okay? The payload is inside of the envelope. You don't know what's in there. It can be 100 megabytes of data. It can be encrypted. It can be encoded in protobuf. You can't see it. It's important, and the receiver will go and open it, and it will then have to be able to tell, but it's not important for transport. What's important is that we have some information about where does this come from, what is the quality of service we're expecting, where does that need to go to, and some other capabilities that are associated with the transport. Metadata is all for the transport to go move things around. The queue reads that. And then your application reads the inside of that envelope. So those are messages. Messages are that. Okay. And I apologize profoundly for having this so small, but I thought at this conference I don't get away without showing you a little bit of code, so I'm going to do that here. And it's really just a blip of how this works. You create a sender, you create a message, and then you send that message, and then you're done. And then you create a receiver, and you receive that message, and then you get the received message, get the body out, and you write it, and that's how complicated interacting with a queue is. That's our client, and other clients in other products, RabbitMQ, AWS, look exactly the same. There's tons more features hidden here, but the simplest interaction with a queue is simply there's a send operation, there's a receive operation. Now, of course, you typically want to go and receive multiple times, right? You want to be ready to deal with many, many messages. So there's also this reactive path where you have this processor thing, and that also exists in many frameworks, which then listens to a queue, and then you go and have a handler, and that handler will then be called, and that handler can then go and move those messages. But what you'll notice here is we have no concept here of methods or parameters, because it's data blocks that may contain the notion of an operation like the subject, but it's really up to you of how you use this, how you want to go and structure your application. You have full control. You can go and use that queue to say, this is a job that I want to go and send, and then pick up that job and process that job. Now, you can go and control, typically in these processors or in these reactive frameworks, you can, for instance, control how many threads you want to have executing concurrently. You can also dial that those number of threads up. If you have a binding for Lambda, Azure Functions, any fast framework, and if you have this with Kubernetes, with Kata, you can go and scale Kubernetes containers up and down using queues because you can observe the length of the queue. You can add and remove these processors very easily. So it's a very easy way to communicate, much simpler with fewer features, but more control than an RPC framework. But it allows you to scale your apps. Where is that used? It's used very extensively in financial services. Basically, everything you do, unless you're into crypto, in that case, sorry. But my euros made 11% on the Bitcoin yesterday, so it's great. Everything else you do, financial trading, ATM withdrawals, everything you do in retail banking runs through queues. There is a standard, and I always forget that long number, but it has to do with 22 somewhere. There's an ISO standard which lists all those message exchanges as contracts. And so that's the latest standard that's being used and driven by Swift. And so all the interbanking communication, all the communication that happens with, for instance, ATMs, all of that happens through queues. Why? Because it's reliable. You don't want to go and lose information. And if you can't lose information, if you can't lose the value of a bank transfer, then what you want to do is you want to go and take the desire to go and withdraw money. So you're standing in front of that ATM, and you're expressing the desire to withdraw money. That is being secured on a disk. And then it's being moved transactionally, which means there's no duplication, but there's also no loss, to one computer and to the next computer and to the next computer, where your ATM withdrawal request is ultimately then routed to your bank. And there's all kinds of mechanisms that sit in the middle of that. So that's all happening through queues because you need to have that communication be reliable, and it needs to work even when there are communication glitches. Your ATM, if you stand in front of an ATM and that ATM has no connectivity, it will give you money. And it will give you money because there are some inherent guarantees in the cash card, in the debit card that you have. And that's why it can do that. But if it gave you money while it was disconnected, then that message that it has stored is cash, because already it borrowed you money effectively on your card, and now it needs to go and do the transaction. But you can now perform this transaction asynchronously with these guarantees that are in the system, and you don't have to have connectivity at all times. If you think about how does that work with paying with a credit card on a plane, well, that's how. Right? Eventually, those transactions get downloaded, and then they get executed later. Industrial automation has a ton of these scenarios. Again, because there are various loads, and because in industrial automation, everything needs to go on a takt. Right? It's all in real time, and you cannot execute real time unless you have schedulers, which are scheduling exactly when work gets done, and scheduling exactly how when work gets done happens through queues. Abstracted, but all those buses are effectively executing through queues. Connected car. When you are giving a command to start the climate control system on your Porsche, as we all have, right? Then that message needs to go and reach that car. How does it reach that car? And just one example of those. Communication with vehicles is notoriously difficult because they sit in terrible networking conditions. Ultimately, they're using German cellular networks, which means they are on edge 95% of the time. And so communication may be difficult, and using queues will help to make that more robust. So it's a terrible idea to go and use RPC-based services for that sort of communication when communication is bad, because you want to be more intentional in going replicating those commands, replicating those messages, and you also want to be very intentional about timeouts, etc. Tons and tons and tons of scenarios where queues are simply a better choice than using RPC. What there also are, they're very great safe network bridges. When you think about DMZs, demilitarized zones, or you think about network segmentation, and a queue is a great way, and that's true for most cloud queues, where you can go and maintain an application in an isolated VNet, and another application in an isolated VNet that has no access from the outside world with RPC called services or networking, but it will go and read from queues. The great thing here is that the queue is a pull mechanism. You attach to the queue and read, and you pull things out, which means nobody can go and push on you. So if you have a queue that can attach to multiple VNets at the same time, you have a super safe bridge where all the communication happens at layer 7 of the network, and there's no way of going to hack around the network segmentation boundaries, but communication still happens. Super common in high security environments to go and bridge via queues. So, some features. Competing consumers is the most important feature. I already talked about that. Exclusive assignment of ownership of a job to a queue, to a consumer. You have many, many, many clients which are coming and want to get something done. There's only 2 processes at the back. Maybe it's a constrained resource like a credit card processor, right? You only get 2 transactions per second or so, right? So you have to go and deal with them, which means you put that behind the queue, and then these competing consumers, which means there's multiple consumers pulling on the queue at the same time, they each get a job, but there's a guarantee that no one job is being assigned to 2 consumers at once. You get exclusive management. And then you can observe the length of the queue to determine how many of these consumers you need. Load leveling is another aspect of this, or a facet of this, where you may get a sudden burst of requests, a sudden burst of telemetry, of jobs, of whatever kind of messages you might get. And you need to go and deal with them, but your system may not be ready for it. Famously, the start of the, who knows Halo, the game? Great. So the start at the launch of Halo 4, it's a few years back, the back end was down for the entire launch day. Nobody realized it because it was all isolated by queues. They could get the back end back up, and then they processed all the data that came through it. Because there was a buffer in the middle that took all the burst information and then stored it, and that ran through our queues, and then they could go and drain it in the back end, and everybody's careers as Spartans was saved. So load leveling makes the load that comes in on the front even because the processors pull. Because the processors pull, you can never overload them. The system will be slow, but it will never be overstressed. And if the system is slow, which means that queue is long, then you scale it up. And again, if you're using Kubernetes, KEDA, K-E-D-A, is a technology which can go and scale the number of your containers based on the length of a queue, and it has a bunch of these kinds of processors, or sorry, those adapters, which can observe multiple kinds of queues. And now I'm going to, also in the interest of time, I'm going to speed a little through a number of slides that I brought. And this is not, again, not a product pitch, but I'm using some of the features that we have as an example of features that other queues have too. So you're sending messages to a queue, and what the queue will do, it will go and create a sequence of them. So it will label them with a sequence number. It will also stamp them with a timestamp of when those messages arrived. So if you need to have an authoritative clock in your system, because we have so many clocks, right, you often need to have a tiebreaker clock. Well, the queue will give you one because the queue will note the time of arrival. You can also go and the way how messages are being delivered to consumers is that it always considers the oldest one that's available and gives that to the next consumer. That's how the order works, right? And that will then cause those messages, when the messages are being handed out, they're exclusively locked to a consumer. And while that consumer has that message in hands, that message is retained in the broker. It's in the state of acquired. And then the consumer can go and decide what to do with it. So it has full control. And if the consumer says, I accept this message, then the message is being removed from the broker, and the work has been done. But the consumer can also say, I want to go and reject that message, and then that message will be put on the side. Putting on the side is done using a dead letter queue. The dead letter queue is another feature that is kind of the bad mailbag that is also typically available in those message brokers. If message processing has an error, you can go and put that message into bad mailbag. If the message has expired, because you can have time to live, and you can go and say, I only want to have this processed within the next 2 minutes, and otherwise please put it on the side, right? Then you can also put that into the dead letter queue. So the dead letter queue is a built-in error handling mechanism that is explicit, that allows you to put bad messages on the side, but it's also just a normal queue, so you can process out of that like a normal queue. Again, that's also existing in very many message brokers. Sessions are the multiplexing feature. I'm going to skip that. Transactions allow you to go and send messages after you've done work to 2 or 3 output queues, and in the context of that session, settle the input queue. If you're going to the cloud and you're familiar with things like database transactions and you wonder where they are, they don't exist, sorry. But if you need to have an approximation of that, message queues will give you that. Because message queues have a mechanism that allows you to go and do a transactional transfer from one context to the next context. And then lastly, not only do these brokers have queues, but they typically also have pub/sub, meaning you can send one message by a producer to a name called a topic, and then you can go and filter them into multiple output queues, which means that's how you can do routing inside of those brokers. Again, you're going to have those slides for reference. You can read all the text yourself. So I just want to go through those things fairly quickly because I didn't want to give you a course that would take a day in all the features. So ultimately, we have multiple of these kinds of infrastructures. We talked today about queue pub/sub brokers, in particular, Service Bus, AWS SQS, SNS, Google pub/sub, ActiveMQ, RabbitMQ, those brokers. There are brothers and sisters of those, which are Apache Kafka, which are event hubs. Those are event stream brokers, discrete event routers, Azure Event Grid, AWS Event Bridge, which are pushing out discrete events. Those are different for different purposes. And if you look for me on YouTube, you will find some talks where I go and explain those. Remember, that's the Kafka thing. Event streaming is not modern. Queues are not traditional. Both are in all systems. Most modern apps use event streaming. RPC, REST, and queues together. And so I hope I was able to give you a bit of an insight into what queues are and where they're useful. And with that, thank you for your attention.
Thank you, Clemens. We have just maybe time for one question. And if queues are suited for very large files, for example, very large blobs of data?
Queues are suited for very large files in exceptional cases when someone has already made that decision, then they are. But I would always avoid it. There's a claim check pattern where you're effectively streaming a file into storage, and then you're passing effectively a link to that into the message queue. That's a more efficient way of dealing with those things, because for a file you will usually have multiple consumers.
Okay, thank you, Clemens.
You're welcome.
In a few minutes we will